In this video, we will be focusing on the materials that we use for the single photon experiment. Let's begin by following the path of the light through the experiment, starting with the laser. For this experiment, we used a laser with a wavelength of 405 nanometers, putting it in the purple wavelength range. The polarization, which is a particular orientation of the electric field of the laser beam, is rotated with a half-wave plate. The laser beam is then directed into the crystal using a mirror. To generate a pair of entangled photons, a barium borate or BBO crystal was used. Because of the structure of the crystal on a microscopic level, when a large amount of photons, such as those from the laser source, hit the crystal, occasionally a pair of photons is generated. This process is called spontaneous downconversion. These photons' energies are entangled. Thus, the energies of the pair must add up exactly to the energy of the 405 nanometer photons. The energies of the two photons are approximately equal, so they each have a wavelength of about twice the wavelength of the initial beam. The two photons exit the crystal at plus or minus 3 degrees from the initial laser beam direction. A pair of avalanche photodiode or APD detectors are set about a meter away to detect the individual photons emerging from the crystals. One of the photons goes straight to the APD. The other photon is directed into a Mach-Zehnder interferometer using a flip mirror. The interferometer is an essential component of the experiment, so let's take a more detailed look at it. An interferometer is a device that is similar to the double-slit experiment. In the double-slit experiment, a light wave or a quanton can take an infinite number of paths from the slits to the screen. A Mach-Zehnder interferometer, on the other hand, only has 2 defined paths that light can take. It does this using mirrors and beam splitters, which are essentially a fancy type of mirror that reflect half of the light and let half of the light go straight through. When the light enters the interferometer, half of the light reflects off the first beam splitter entering path 1 and half continues through onto path 2. Mirrors are then placed upon path 1 and 2 to reflect the light into a square. The final beam splitter is then placed on the overlap of path 1 and 2. Half of the light from path 1 is transmitted to output 1 and the other half is reflected onto output 2. For path 2, the opposite happens. The net result is that both beam splitter outputs have light from both path 1 and path 2. Since there are 2 paths in the system, light wave and quantons can interfere. For interference to happen, 2 things are necessary. Firstly, the 2 beams must be aligned, which means that at the outputs of the second beam splitter, the beams must be coincident. This can be achieved by adjusting the angle of the mirrors and the beam splitter. Secondly, for the interference pattern to happen with single photons, the path lengths of the interferometer need to be essentially identical. If the path length difference is large, the light from each path won't arrive at the beam splitter at the same time, meaning it won't be able to interfere. Furthermore, if the 2 path lengths are different enough, it will give information about which path the photon took, which would destroy the interference pattern. In order to achieve identical path lengths, a white light and an optical spectrometer, which is something that spreads out light based on wavelength, was used. White light is composed of many different wavelengths, so it only has a very small range of path length differences for which interference can happen. We can experimentally determine the path difference from white light spectrum by taking advantage of the Alford-Gold effect. For a path difference delta L, there will be a modulation in the intensity of the spectrum with the spacing between adjacent maxima given by the equation displayed on screen. We see that as the path difference goes to 0, the spacing between the adjacent maxima in the spectrum goes to infinity. Practically, we did this by adjusting a mirror side to side until we found interference fringes. The further away the fringes, the closer the difference between the two path lengths was to zero. In the experiment, a PZT, which is a piece of ceramic that expands when a voltage is applied, was added into the mount of the movable mirror. A computer program was then used to incrementally increase the voltage on the PZT, shifting the path length difference slightly and causing the interference pattern to shift. After the photon goes through the interferometer, it's directed back to the initial 3-degree line using 2 additional mirrors. From here, it travels to the second photodiode. The photodiodes have a filter in front of them which lets light through with a wavelength of 795 to 825 nanometers. This filters out most of the room light. In this experiment, we were attempting to collect data about how the intensity of light that went through the beam splitter varied as the voltage applied to the PZT, and therefore the path length difference was varied. Lengthening the path length difference should shift the interference pattern, going from constructive interference, where the rate of coincidence detections is high, to destructive interference, where the rate of coincidence detections is low. A graph of the rate of coincidence detections versus path difference follows a sinusoidal function.